Streaming. Got it. And we're going to record the cloud. Okay, welcome everyone to our next Water, Wetlands, and Watersheds seminar. Apologies for those of you who didn't know it was going to be virtual. We'll try to do a better job of that next time. But we are lucky enough to have our colleague and friend, Sandra Guzman, is presenting for us today. So I'll introduce you and then you can share your screen, Sandra. So Dr. Sandra Guzman is an assistant professor in the Department of Ag and Bioengineering. She's at the Indian River Research and Education Center in Fort Pierce, Florida. Any of the undergraduates, are you from Fort Pierce? Anyone Fort Pierce? No? Been there? It's a nice stop. I mean, I know the stop on the turnpike, right? Dr. Guzman has a PhD in biological engineering from Mississippi State University and an MS and BS in agricultural engineering from Universidad Nacional de Colombia. Her research program involved the implementation of sustainability solutions for agricultural water management. And she also has a robust extension program that focuses on improving stakeholders' capacity to make informed water management decisions about crop production using knowledge and data-based approaches. So Sandra, thank you so much for presenting to us today, and go ahead and share your screen.
All righty. Thank you everyone for being in person and online today. Let me see. Let me know if you can see my screen before anything else.
That looks good.
Okay, perfect. So today I will talk about a little bit of challenges and opportunities in terms of implementing precision irrigation in the state of Florida. But I will focus on the work and the progress that we have been doing with here in our research and extension lab in Fort Pierce. So you will hear a couple of examples for citrus production. I was planning to give you a little bit of the taste of sweet corn and vegetable production, but I'm gonna leave it for later. So before anything else, let's talk a little bit about precision irrigation and what is smart precision irrigation. So smart and precision irrigation have been used mostly like recently over the last 10 years, and it's gaining a lot of popularity in terms of improving the efficiency of crop management practices. So in this case, we will focus on water and nutrients, but mostly focus on water quantity. So when we talk about smart irrigation, similar that's cell phone, we think about having apps or having Internet of Things-based systems that can help us make a decision, or that is giving us directly a recommendation. So over here, you will see multiple options. So you will have sensors, you will have apps, and these kind of systems are basically available for use. So I'm not going to focus on apps or drones or images coming from basically data coming from above. I'm going to focus more than anything else on the use of sensors, which are kind of the precision agriculture sensors that are mostly used in the state of Florida. So if you have questions about why I'm not focusing on smart apps, if we have maybe smart apps available, we can discuss that after the presentation. I will be happy to talk about it. So in terms of precision irrigation, mostly precision irrigation is related to variable rates. So when you hear variability or variable rate, we are talking about precision irrigation. So in North Florida, systems with a center pivot irrigation and row crops, let's call it soybean, corn, and all of these cropping systems can be managed with precision irrigation. So these systems are based on soil variability, plant variability, weather variability. So the image that you see here on this side have multiple soil types, and a precision irrigation and a precision management system should be able to give the precise amount of water for this soil, for this and other soil, and for the rest of the field separately. So that is the difference kind of between precision irrigation and the similarities between precision irrigation and smart irrigation. So these kind of tools are tools available for the decision-making process. So I want to stop a little bit here and say and ask you to think as a plant growing person. You may have plants in your house, potted plants, and you may have had questions on when to water it, what happens if the leaf is yellow, what happens if you see a gnat or a little pest or something like that. So having information to decide if you should put more water, less water, more nutrients, less nutrients, is kind of what precision irrigation is made for. So in terms of opportunities for adopting precision irrigation, we have three main opportunities. Number one, having access to real-time data for decision making. So if we have a potted plant at home and we have real-time coming from multiple systems, data coming from multiple systems, then it will be way easier to make a decision and to see how to manage those nutrients and that water efficiently. At the same time, if we have a better use of that water and nutrients, then we can increase economic benefits. And here is kind of the well-being. If we are moving from the potted plant at home to an agribusiness, having the increases in economic benefits and basically societal well-being is kind of the goal of these kind of systems as well. And indirectly, we can work with nutrient movement, because if we reduce the amount of water applied, then the nutrients are moving less into freshwater systems. So we can reduce or could reduce runoff and leaching if we incorporate only precision irrigation practices or smart irrigation practices. So talking about access to real-time data for decision making, I just realized that this is not something happened with the PowerPoint, so this is an older version of my presentation. I apologize about that, but in terms of having access to real-time data for the decision making, this is a picture of what kind of sensors and what kind of systems a farmer could have in their field. So they have many sensors, including the rain gauge and all of these sensors in the field. On top of that, they may have an infinite number of sensors. We don't know how many, but all of those are systems that the farmer will have to manage nutrients and water. And this is only nutrients and water. So in your potted plant, you may have a soil moisture sensor like this one, for example, just to see what is the water status of your plant. And then you may have to have, if your plant is outside, you may have to have a weather station. If your plant is inside, we can make an assumption that the thermostat in your house is kind of controlling the temperature and controlling the humidity of your house. So then you will have to check, hey, the thermostat in your house, the soil moisture app in your cell phone, and try to figure what is the water status. So for the farmer, in this case, they will have to check if the weather station is from one brand, they will have to check for with the software with that company, like how is the weather looking like, and then moving into the software for soil moisture and check the soil moisture in this case. So they will have to move into what is happening with the rain, what is happening with the relative humidity, what is happening with the soil moisture. So then the challenges start right here, because the data transfer and the data visualization, number one, is in multiple platforms. Number two is being managed by the company. So if the company makes an agreement with the farmer, then the company is managing that data. Some companies own the data, even if the farmer is the one collecting the data. Other companies may have some agreements where the farmer owns the data. The other challenge, and Daniel Palacios, one of our technical assistants here, works with that, is that the installation of sensors is difficult. Gaining trust in the sensor is difficult. Doing troubleshooting, I mean, we have to do troubleshooting frequently, because there are things that could happen with the sensors. So all of those troubleshooting and maintenance issues have to be basically an extra load for the farmer. So they have to become technicians if the EOF IFAS system is not with them. Other challenges is that usually we work with the extension office, and the extension office is key in the transfer or whatever technology we create into the field and into implementation. And then they work for not for 6 months, nor for 2 days. They work for many years with the farmer, showing the sensor, showing the system, establishing trust, processes of trust, basically. And then a new release of the latest and greatest technology that the super smart engineers bring up to the market appears. So the learning process will start again for both the extension agent and the farmer. So the learning curve kind of gets reset if we incorporate new systems that are just prescriptive systems. I will leave this discussion for the end for sure. So
does everybody know what extension is? Like, I know our ag student friends know what extension is, but does anybody not know what is extension? Okay, I got a couple of hands here, Sandra. So we got people who don't even know what the capital E on extension even means. So just maybe give us.
Oh, beautiful. What a wonderful opportunity to talk about extension. So extension is teaching, and it's teaching students that could be 5 years old or 80 years old. So it's unconventional teaching. So basically transfer knowledge that is creating from research up to the industry. So in this case, transferring whatever knowledge you are doing as a student, or all the scientists at the University of Florida are doing, transferring that knowledge in words that anyone can understand, and in educational programs that can be implemented to have either higher economical well-being, social well-being, or better environmental impacts. So in terms of water resources, we are looking for higher yield from the ag side. We are looking for environmental benefits, so reduction of the impacts of any ag practice into the environment. Not sure if that was clear. It's unconventional teaching, but basically we talk, we sit with people, we sit with agencies. It's not only the farmer. There are industries, there are basically local offices or any decision maker that wants to learn about the technologies that we have.
All right, thanks so much.
Yeah. So the goal in general is that the decision support system, the software, the technologies, the innovations that we are creating should be easy and practical enough to be implemented by a farmer or to be implemented by, let's say, an economist or that is located in Tallahassee, or being easy to use for someone that has a background that is not in engineering. So, for example, a horticulturalist or someone that does ag education. So these kind of systems should be easy to understand and practical enough that can give us the opportunity to really transfer the new technologies that we are developing. So in our team, we started developing a decision support system that is called Eric Monitor. I hope I can show it to you. Okay, so it's going over there. So in Eric Monitor, we have a simple display. It looks super simple, it's not simple for a new user. So remember that you are in your grower, farmer, or mindset, and you see this kind of image. So this is the common image that a farmer see when they want to know the soil water status of their field. They see a bunch of graphs without having an engineering background, and they have to make a decision in less than 30 seconds so they can move on with their lives. So I hope you made a decision already.
Irrigate.
How much?
1 inch.
Why?
I don't know.
Exactly. So if we may irrigate 1 inch, 2 inches, 3 inches. So we may, even if we have this information available, we may rely on our own eyes as the best sensor to say, well, it's kind of dry. I'm gonna put water, and I'm gonna put it until the soil looks wet, and that's pretty much it. But what about utilizing this? So, so the extension office, back again, they have been working with farmers all across the state of Florida to help them understand what these graphs mean. So over here on top of the display, we have soil water content, so how the water status of the plant. In the lower side, we have electrical conductivity. Nobody knows why electrical conductivity is here. Farmers are not using it up to now, but it's something that is available. Many companies have that available. So coming into the upper side for soil water content, we have 2 graphs over here that represent the upper and lower sensor across the soil profile. So in this particular case, the farmer has 2 sensors at 2 different depths and is showing us the water status of the soil. So focusing on the ups and downs on this graph, any up represents water application. So we can say that here there was an irrigation event. So they apply water here. And the yellow one is the bottom sensor. So in the lower side, the red one is the upper sensor. So we have more water coming from more water in the lower sensor and less water above. So it may happen that the farmer irrigate and then the water move, or that there is water table moving from below. So one or the other case. We start looking at electrical conductivity as more detail, because electrical conductivity or volumetric ion content is a representation of the salt content of the soil. So our hypothesis, and I will show you a little bit about what we did, is that, hey, if we have a fertigation event, fertigation is basically where you mix fertilizers with water. If we have a fertigation event, we may see spikes in electrical conductivity after that fertigation event. And by just having a soil moisture sensor, we may be able to assess where the nutrients are going, if they are staying in the field or if they are going to the Indian River Lagoon in the case of where I am located. So this is one of the displays. We work with this system with 3 farmers. So this is a collaboration with farmers. The farmers had outdated systems and they wanted to have the latest technology. So we started with this display system for them. Then they told us, we hate the graphs. You are an engineer, you are always showing us the graphs, and we hate graphs. And equations, yeah, they never want me to show a graph or an equation. So I was like, okay, so what you want? So we incorporate this system that over the left side that basically is telling you what is the status of your soil moisture at the moment where the sensor is measuring. So over here, if you see green, that green color means that the water status of the soil is okay. If it goes to yellow or to red, then water has to be applied. If it goes above the blue up to the purple line, then we have overwatering or the effects of a hurricane season or an extreme rain event. So we start showing only this part, and then they became familiar. They like it, but they wanted the graphs back. So they were like, okay, we like it. We know how to use it. Now we want to see more details. So because of that, we work multiple displays. So we have a total of 5 displays. This is the most basic display, but we have 5 displays that go from more familiar systems to less familiar systems, that go from rapid movement of water to slow movement of water. This system is also a system that helps, especially with this overwhelming issue. And you may have lived that in your own life, day-to-day life, when you have like the smart light, the smart thermostat, the smart thing, and 20 apps in the cell phone. And it's like, oh my gosh, I have to go to this app to update it, to move here, to move there. So the idea with this particular system is that we can have sensors from multiple companies just providing us sending the data up to here, up to this software, so we can have a full spectrum of what's going on with all the sensors, weather and water related, in only one platform. So at this point, as I mentioned, 3 growers are testing this system, and they are giving us a lot of comments, and we are coming back and forward with them, trying to improve this system. This system is still incorporating, for example, the weather forecast as part of the decision support system to help have an image in terms of rain. But we are also using Irrig Monitor as a system to have educational programs, centralized educational programs that can go all across the Strait of Florida and the multiple range of environments, crops, and knowledge. So if we can have one system, we will have one educational program that will go for industries in North, Central, and South Florida. So that is what we are using Irrig Monitor for. Then in terms of the second challenge of increasing, the second opportunity, more than challenge, increasing water use efficiency and economic benefits, we continue working with farmers here in the Southeast part of Florida. And we started a collaboration with a lemon farm grower, and we started this project in 2019. So it's the fourth year of the project, and just evaluating best management practices. So the ground cover, you see that there is a comparison in this picture between bare ground and ground cover. So this ground cover, the farmer basically put, like, I think at the time, 50 acres of land with this black ground cover to protect the root system from a pest that is called the diaprepid root weevil. That was the idea. But then our team went and helped installing soil moisture sensors and automation, so they could manage their irrigation from their cell phone. And then we saw these ground covers, and we start asking what is happening, like what is going to happen with the water and with the water movement if the irrigation system is micro sprinkler. So a micro sprinkler irrigation system basically works as a little shower or a little rain on top of this plastic ground cover. So the water is coming from above the cover, is not coming from below. The same with nutrients. Everything is coming from above. So we start doing the evaluation of physiological responses, or we start evaluating where the water was moving, where the nutrients were moving, if the nutrients were really passing through this ground cover or not. Just as a clarification, the ground cover is not 100% plastic. It's a blend of wood, plastic, and other materials, and is knitted in a way that is what the company said at the time, that let pass the water, that let pass nutrients and all of that. So we start testing that. The results that I'm showing here are from 2019 up to 2021. We just received the results for 2022. We ended up analyzing that recently, but it's pretty similar to the results that we got in 2021 with a little caveat. So the bars that you see over here are canopy volume. We work with trees in a commercial field. So the only thing that was changed was the water application and the cover itself. So our team was calling the farmer every week, giving recommendations of water application for the ground cover and for the bare ground. Over the 4 years, we track, number one, the farmer decision. So if we recommend 2 hours of water, did they apply 2 hours or 4 hours or 3 hours? Or did they apply more frequently, less frequently? So we start working on collecting data on how the communication process between the researcher and the farmer went. At the same time, we evaluate physiological development, so plant growth. In this case, you are seeing trunk diameter with the lines here, and canopy volume. So consistently, we had significantly higher canopy volume for the covered treatment compared to the uncovered treatment. Consistently, we had a higher trunk diameter in the covered treatment compared to the uncovered treatment. What this means, that is reducing that the ground cover itself and the irrigation management that we are doing is helping reducing the stress of the tree. Having less stress helps with, at the time we were thinking, that helps with higher yield, and it did. With the results that we got last year, we also have significant differences in yield. So we have, this is weight per tree. So basically, we collect the weight per tree, and we did comparison between the cover and uncovered treatment. And we found that that the cover treatment was having higher, like highly significant weight compared to the uncovered treatment. So this part was kind of the most important part for the farmer. After this moment, then we start the conversation of, okay, soil moisture sensor irrigation works, the ground cover work, like whatever system that your researcher are putting in your mind are really working, because we increase yield, which represent economic outcome in a significant level. Some things that we have pending in this study is over here you see the differences between the cover and the uncover and the cover treatment per repetition. We had 5 repetitions, and one of those repetitions was giving us like very extremely high yields. It turns out that the soil in this area is a little bit different, and that can be a high influence on the responses that we are seeing. So other results, I mean, we have to incorporate the soil variability into the equation. We were not including it at the time. And the last one, so precision irrigation could reduce runoff and leaching. So one of the things that we are seeing, besides these issues with the displays or the information and how the information is being practical or not for the farmer, is that there is a lot of data being collected with these sensors and with the software, but there is a data overload at the same time. And one of the data overloads that the farmers are getting are related to this electrical conductivity and volumetric ion content. So if you remember the short video that I show at the beginning, there were some peaks in soil moisture and some peaks in electrical conductivity. So our hypothesis for this particular study was that electrical conductivity, values of electrical conductivity may be able to track the movement of phosphate or the movement of nitrogen or nitrates in the soil. Our team went and collect soil core. All of this study was made in the lab. And it's a study on progress, so I'm not going to show you like conclusions over here. We are still working on this. This core was collected from a field that is called the salt block. So it was irrigated at the time, like I think 7 years ago, with ocean water. So high levels of salt in this particular core. And then in the middle, it has a soil moisture probe. So each one of the lines that you see over here is one sensor. And then the core was set vertically, and solutions of water and phosphate were applied. So a control with still water, 10 parts per million and 100 parts per million of phosphate were applied into this core. Then the measurements from the sensor were made every 30 minutes, and we work this core for 24 hours. After the 24 hours, the core was basically the multiple samples for each one of the lines that you see here were sent to the lab to see where the phosphate was for comparison. We also had a control soil that is 100% sand, pure sand. So a little bit of the results that we got from this preliminary study are over here. So you see how graphs can be so overwhelming. So the farmers have the same all the time. So this set of overwhelming graphs on the right side are showing soil moisture. On the left side are showing volumetric ion content or electrical conductivity, let's put it as well. They are related. The upper two are showing the upper layers of the soil, the lower two, the lower layers of the soil. So each one of the colors represents one of the sensors across the profile. So companies that that work with these sensors now are telling the farmer that if they look at this data, and if the volumetric ion content and the soil moisture are decreasing at the same time, that means that they are losing nutrients, that the nutrients are moving down, or they are getting out of the area where the sensor is located. And vice versa. If the volumetric ion content and the soil moistures increase at the same time, it means that it's gaining nutrients. So based on this, on this core particularly, we saw that at this time we had losses in the upper layer and gaining on nutrients at the lower layer. And that's pretty much what we got. When we went into the statistics, nothing was conclusive, not even the results that we got from the lab. So there are so many questions that are open here for this particular set of data. We are now, instead of focusing on how the volumetric ion content or how the salts go up, we are now focusing on when those salts are moving from one side to the other. So we are switching kind of the graph and moving the y-axis up to the x-axis and vice versa, so we can really have an idea of what is happening in terms of time, because in terms of the spikes, the sensor itself is not being able to sense the movement of phosphorus all across the profile. So as I mentioned, this is a work in progress. We have to work on strategies to highlight better what is happening with volumetric ion content. Definitely improve the visualization platforms. If volumetric ion content is not the answer, it shouldn't even be available for visualization. We are also calling for researchers that develop sensors, and researchers that are working on developing phosphorus and nitrogen sensors to incorporate those sensors in the systems that are already in the field. So if a farmer already have a soil moisture sensor and they are familiar with it, what about if we incorporate the phosphorus sensor over there? What about if we incorporate the nitrogen sensor, not have it separately, so we can prevent this overload? So as I mentioned, an optimal water management strategy should have a technical, a socioeconomic, and an environmental balance. So it should have the balance between those three. In terms of technical, we have the sensors, the software, the automation. In terms of socioeconomic, Florida has some incentives and subsidies so the farmer can utilize the technologies. But if we can prove with the technical developments that yield can be increased, that's great. In terms of environmental, we have limits, regulations. We have a little bit of work to connect what is happening from the environmental side and what is happening with the crop production side, in order to have a big picture of where the nutrients are moving and if the solutions that we are creating are really useful. So in terms of challenges for adoption, we have to keep working on increasing the trust of technology efficiency from the farmer. We have to start thinking about systems that are user inspired and that have the end user, in this case the farmer or the decision maker, as the one testing and as the one evaluating this, the technologies that we are developing. So we can move on in terms of progress and to do a better management of water and nutrients. And finally, having these systems that are user inspired will help us also to incorporate, to transfer this information to the environmental agencies, to say, hey, these systems are really working. We are doing a good job on managing nutrients at the field level, or we are not doing a good job on managing those nutrients. But that connection between the environmental and the crop management has to be there. And the extension office and the ones that are transferring knowledge to layback audiences are the ones that are key in this work as well. So with that, I'm gonna leave a little bit of room for questions, and we can continue discussing this topic. But if you want to take let's say a take-home message, as researchers, we really have to think about the end user and who is going to use the solution that we are trying to test and provide when we are developing any kind of technology. If we continue creating solutions, in my case, that are from engineers to engineers, I mean, we will have to have one engineer per farm at least, so we can prove efficiency.
All right, thank you, Dr. Guzman. Let's give a round of applause. So I'm going to bring you back here, and so you're projected on the screen. Just aware. Let's see. And we'll take questions from the room first, and then I'll check the YouTube and the Zoom. So start with any student questions, please. Yeah, go ahead, Pietro.
So I was curious about with that the fabric kind of mulch covers. So you had said that they're originally there to prevent weevils, and that the results were showing that there was a higher crop yield with the covers. Do you think that could have anything to do with weevils? You know, like they're doing their original job?
Yes. So we in this we collaborate with the root biology lab next door. So we also install rhizotrons that are basically that are tubes, so where you put 360 cameras, and that 360 camera gives you an image of how the roots are growing and if there is any sign of stress from the roots. So comparing the uncover and the cover treatment, we got, in terms of main roots, we did not have significant differences. We were expecting significant differences. The reason why we think we did not have significant differences between the ground cover and the bare ground is that the bare ground basically the 5 trees that we got per repetition, we have a total of 50 trees for all the repetitions, were surrounded by the ground cover. So that is our hypothesis. Unfortunately, I cannot talk a lot of details about the root physiological growth, but definitely there was an influence. We did not find that there were significant, though. In terms of water, last year especially, we found that the uncovered treatment, the one without the cover, actually had a better water use efficiency. and we were asking why. It was because the farmer forgot to weed that year. For multiple months, they didn't weed the uncovered treatment, and those weeds serve as a mulching system. So they were actually helping us with water savings. They were competing in terms of nutrients with the tree. So we have losses in terms of nutrients because they were going to the weeds. We were gaining in terms of water savings. So it's a really good question because we also have to take in account the trade-offs between, okay, what is going on for pests, for nutrients, for water, not only one response.
Thank you.
All right, other questions from Zoom? Yeah, quiet YouTube, so I'll go to a question in the room, so go ahead.
I remember several years ago, about the time that, crop circles were going in and everyone, and they seemed to be just great, but they used a lot of water. And so they came up with more precise use of the water. But then water use actually went up because the farmers were putting in more units since they had more water that they could spend in their allotment. And so there's obviously not much loyalty to the concept of saving water.
So Simon, do you think there's kind of like, perverse incentive, you save the water, so then you just expand that, you extensify, because you become more efficient, so you don't end up saving at the landscape scale.
I'm not sure I understood the question very well, but let me rephrase because now I have two sides of the question. So trade-offs between, hey, having too much efficiency and then too little on the environmental side. That was the question. Or the question was that, hey, we have so much water that what's the point of focusing on saving water?
Well, the farmer has an allotment, and so they use that allotment of water. And when they find that they're saving water, they then expand their crops so that they can use that additional water. And so that doesn't say much about their interest in saving water as a globally good thing to do.
Well, at that point, I think is that where the environmental side comes to play. If there is a water allocation, but at the same time the crops are expanding, yeah, there is higher efficiency, but we are not going to see the outcomes in terms of the environmental side ever, because basically crops will continue expanding and expanding, or we may have a higher plant density, for example, that it happens. So this is something that we have to continue working on, and incorporating measurements like, okay, we have the total maximum daily loads. We have some information, really good information from the environmental side, where we know that there is a limit as well. So besides the water permit or the water allocation, we should incorporate other measurements into the equation that are not being incorporated at this point. In terms of production, I mean, if you have an agribusiness, you will tend to be as optimal and as efficient as possible, expanding your business as much as you can, of course.
So I think you'll see this a lot across all of our presentations. There's like the carrot and the stick. This is like incentivizing or making better decisions available, and perhaps supporting them, like paying farmers to use these technologies, versus the stick, which is there's a regulation and you can't do this. You can't grow this much, right? And so there's this trade-off where when you incentivize and make things more efficient, that's great. But if it's unbounded, then they just be more efficient everywhere, and you can expand the footprint. Same with development, same with anything else. And then other folks that might want to sit over here and say, well, the farmers are ruining everything, so we're going to just stop doing, right? and then you're gonna regulate out an entire industry, but you're not going to. And so you're gonna see like bouncing back and forth, camps that think you should incentivize smart technologies versus camps that think you should stop activities. And we can do more research like continuously about this. You've seen it, right? All right, any last questions?
Yeah,
for Dr.
and
Please go ahead.
And the other thing, I mean, we can continue with this precision ag technology, and we didn't talk about AI and machine learning, which I mean, I came to the area to work in machine learning, and look at me, I'm still in the sensor side. So what if we continue with this efficiency process and we get fully automated? Then if we have full automation, then we will have we will have everything fully controlled, and then that will help us having higher yields, higher production, higher everything, and everything accounted for. But the social well-being is something that also have to be taken in account. So carrot and the stick for sure.
Yeah. All right, let's give another round of applause to Dr. Guzman. Thank you. For next week, I'm pretty sure, I'm like 99% sure we're virtual. Next week, we have Devi Kajam. He's also from one of our research and education centers. So I'm pretty sure he's going to present virtually. You're welcome to come to the room. If you come, let's bring some snacks. If you're going to come, it's like watching TV, right? Otherwise, you're welcome to watch it on Zoom. And I gave some comments to some of you on your write-ups, just about a little bit about form and content. So please check out those comments. Otherwise, we'll see you next week. Thank you, Sandra.
Thank you.
Cheers.